An average modern car contains about 200 sensors producing data in 195 different formats. This fragmentation is why most companies fail to create valuable IoT products despite sitting on mountains of potential insights. In the next 60 minutes, you'll learn the step-by-step process for turning this chaotic data ecosystem into structured products that customers will pay for. No advanced degree in data science required. The data economy, IoT as the new oil. What if I told you that the most valuable resource in the world today isn't gold, real estate, or even traditional oil? In fact, it's something that surrounds us constantly, something that's being generated at an unprecedented rate by billions of connected devices around the globe. I'm talking about data, specifically the massive streams of information flowing from Internet of Things devices that are transforming how we understand and interact with our world. This isn't just a theoretical concept. Major companies and economic analysts now recognize data as the defining resource of our era, the new oil of the digital economy. But this comparison goes deeper than just acknowledging data's value. Like crude oil, the raw data streaming from IoT sensors and devices isn't immediately useful in its natural state. It requires sophisticated processing to unlock its true potential. Think about how the oil industry works. Crude oil must be discovered, extracted from the ground, transported to refineries, processed into various products like gasoline and plastics, and finally distributed to consumers. Each step adds value and transforms the raw material into something increasingly useful. This same value chain applies perfectly to IoT data. The challenge facing most organizations today isn't a lack of data. It's quite the opposite. Companies are drowning in information from connected devices, industrial equipment, consumer products, and environmental sensors. These vast reserves of digital information represent potential value, much like oil fields represent potential energy. But here's where most organizations fall short. They lack the equivalent of oil refineries for their data. Consider a manufacturing company that installs sensors throughout its production line. These sensors might capture temperature readings, vibration data, energy consumption, and dozens of other metrics, generating terabytes of information. Yet, without the proper infrastructure to process this information, it remains just numbers on a server, providing minimal value beyond basic monitoring. This is where the oil analogy becomes particularly instructive. Just as crude oil isn't useful until refined into specific products, raw IoT sensor data offers little value until it undergoes processing stages that transform it into actionable insights. The companies that succeed in this new economy are the ones building sophisticated data refineries, systems that can clean, normalize, analyze, and transform raw information into valuable products and services. The economic implications of this transformation are profound. The gap in value between unprocessed IoT data and refined data products can be orders of magnitude. Think of a smart thermostat company. The raw temperature readings from millions of homes aren't particularly valuable on their own, but when properly processed, this data can reveal patterns in energy usage, predict maintenance needs, or enable service providers to optimize energy distribution across a city grid, each representing substantially more valuable applications. We've seen numerous organizations invest heavily in IoT deployments only to be disappointed by the returns. A classic example is a large utility company that spent millions installing smart meters throughout its service area. While the meters provided basic usage information, the company failed to develop the analytics infrastructure needed to derive meaningful insights from this data. The result? Minimal improvements in operational efficiency and no new revenue streams, despite sitting on a potential goldmine of information about energy consumption patterns. This pattern repeats across industries. Retail chains install customer tracking sensors, but can't effectively analyze shopper behavior. Healthcare providers collect patient monitoring data, but lack the tools to identify early warning signs of complications. Agricultural companies deploy field sensors but can't translate soil readings into actionable recommendations for farmers. As Thomas H. Davenport wisely noted, information in this economy has been called the new oil, but like oil, it needs some work. It needs to be refined and distributed and consumed. This observation cuts to the heart of the challenge. Organizations must recognize that collecting data is merely the first step in a complex value chain. The companies succeeding in the IoT economy have built comprehensive infrastructures that mirror the oil industry's extraction, refinement, distribution model. They're not just collecting data, they're transforming it through sophisticated processing pipelines that clean, normalize, analyze, and contextualize the information. They're creating user-friendly interfaces that make insights accessible, and they're distributing these insights through channels that reach the right decision makers at the right time. Take Rolls-Royce's jet engine business. They have transitioned from simply selling engines to offering power by the hour, a service model where airlines pay for engine uptime rather than the physical product. This transformation was only possible because Rolls-Royce built sophisticated data processing capabilities that can analyze the terabytes of information generated by their engines during flight. By refining this raw operational data into predictive maintenance insights, they've created an entirely new business model worth billions. Similarly, John Deere has transformed from a traditional farm equipment manufacturer into an agricultural technology provider. Their equipment now collects detailed soil and crop data, which is processed through advanced analytics systems to provide farmers with precise recommendations on planting, fertilization, and harvesting. The raw sensor data becomes refined agricultural intelligence, a product far more valuable than the original information. The key difference between these success stories and the companies struggling to monetize their IoT investments isn't the quality or quantity of data they collect. It's their approach to refining that data. Successful organizations have developed structured methodologies that systematically transform raw information into valuable products and services. This is where a systematic framework becomes essential. Just as oil companies have established processes for turning crude oil into gasoline, organizations need structured approaches to convert IoT data into products. This isn't something that happens organically or through ad hoc analysis. It requires a deliberate end-to-end process that addresses every stage of the data value chain. The companies leading in IoT are treating data as a product in itself, not just a byproduct of their operations. They're investing in data infrastructure with the same rigor they'd apply to manufacturing facilities or supply chain logistics. They're building teams with the specialized skills needed to extract value from information. And they're creating governance structures that ensure data quality and accessibility. Most importantly, they recognize that data refinement isn't a technical challenge alone. It's a business transformation that touches every aspect of the organization. The parallels to the oil economy extend beyond the technical processes to encompass organizational structures, business models, and strategic planning. Just as the oil industry evolved specialized roles from geologists who locate deposits to chemical engineers who optimize refining processes, the data economy is creating new professional specialties. Data engineers, machine learning specialists, and IoT architects are the petroleum engineers of this new economy, applying specialized expertise to extract maximum value from raw information. The 7-stage data refinement framework. While these specialized roles are critical for handling IoT data, there's a fundamental reason why tech giants like Google and LinkedIn consistently transform raw information into valuable products when most organizations struggle to generate even basic insights. The difference isn't just talent, it's structure. These leading companies follow a comprehensive framework that brings order to what would otherwise be chaos. Think about it. When you have millions of sensors generating petabytes of data, casual or improvised approaches simply collapse under the weight. Success requires a methodical system, a blueprint that guides the entire process from initial concept to market delivery and beyond. This blueprint has evolved significantly since its origins. Back before the internet dominated our lives, researchers Meyer and Zach developed a 5-stage model for information product development: acquisition, refinement, storage, retrieval, and distribution. This framework was revolutionary for its time, establishing a systematic approach to handling information as a product, but it was designed for a world where data was primarily structured and relatively limited in volume. Fast forward to today's IoT landscape, and the challenges have multiplied exponentially. The original framework, while foundational, simply wasn't built to handle the complexity of sensor data from billions of connected devices. The volume of information has exploded, the variety of data types has diversified dramatically, and the velocity at which new data arrives has accelerated beyond what anyone could have imagined when the original model was conceived. To address these new realities, Modern experts have expanded the original 5-stage model with 2 critical additions that transform it into a comprehensive 7-stage framework specifically calibrated for the IoT era. These additions fundamentally change how organizations approach data products, moving from a linear process to a cyclical system that continuously evolves. The first critical addition happens before a single byte of data is collected, product conceptualization. This preliminary stage focuses entirely on defining the specific problem the data product will solve, rather than starting with the question, what data can we collect? Successful organizations begin with, what value do we want to create? This shift in perspective ensures that all subsequent efforts align with creating something genuinely useful rather than just amassing information for its own sake. During this conceptualization phase, teams identify their target users, determine the specific decisions those users need to make, and define exactly how data-driven insights could improve those decisions. Only after establishing these parameters do they begin considering which data sources might provide the necessary information. At the opposite end of the spectrum, the second major addition is the market feedback stage. This final component creates what engineers call a closed-loop system, one that doesn't simply deliver a product and consider the job done, but instead continuously gathers user feedback and market response to refine the offering over time. LinkedIn's People You May Know feature exemplifies how powerful this feedback loop can be. This feature was initially rejected by product managers but was championed by data scientists who insisted on testing with users. Through continuous refinement based on user behavior and preferences, it eventually became responsible for driving substantial user growth on the platform. Without this feedback mechanism, the feature might have remained a rejected concept rather than a central pillar of LinkedIn's success. Together, these 7 stages, product conceptualization, acquisition, refinement, storage, retrieval, distribution, and market feedback, create a comprehensive system for transforming raw IoT data into products that deliver genuine value. Each stage addresses specific challenges posed by IoT information. In the acquisition stage, organizations must handle the sheer volume of data streaming from countless sensors, often using edge computing to process information at the source before transmission. The refinement phase tackles the variety challenge, standardizing diverse data formats from different sensors and manufacturers into coherent, usable information. Storage systems must be designed to accommodate the velocity of incoming data, with strategies for managing both hot data, requiring immediate access, and cold data, historical information accessed less frequently. Retrieval mechanisms need to provide rapid access to specific information amid vast repositories, often using specialized time series databases optimized for sensor data. Distribution requires delivering insights through multiple channels, from dashboards and mobile apps to API integrations and automated alerts, to ensure information reaches users when and where they need it. And finally, the market feedback stage completes the circle, collecting usage patterns, user suggestions, and performance metrics to inform refinements to the existing product and inspire new ideas for the conceptualization stage. What makes this framework particularly powerful is its cyclical nature. Unlike manufacturing processes that follow a linear path from raw materials to finished products, data product development functions as a continuous loop. Each cycle through the system generates not only a refined product, but also new insights that inform the next iteration. This continuous improvement mechanism is especially crucial in the IoT space, where both technology and user expectations evolve rapidly. A static approach quickly becomes obsolete, while a cyclical system can adapt to changing conditions and incorporate new capabilities as they emerge. Organizations that implement this 7-stage framework gain a significant competitive advantage. Rather than drowning in a sea of unstructured data or pursuing random insights without clear purpose, they maintain focus on creating specific value. Their data collection efforts remain targeted towards solving defined problems rather than accumulating information indiscriminately. The contrast with typical organizational approaches is stark. Many companies invest heavily in sensors and data collection infrastructure without first defining what problems they're trying to solve. They amass terabytes of information without the refinement processes needed to extract meaningful insights. They build elaborate dashboards that display data without actually informing decisions, and they rarely close the loop by systematically gathering feedback to improve their offerings. The seven-stage framework provides the structure these organizations lack. It transforms chaotic data management into a disciplined product development process. It ensures that investments in IoT technology translate into tangible business outcomes rather than expensive experiments without clear returns. Stage 1. Product conceptualization, identifying the metric of interest. This disciplined approach begins with a deceptively simple question that separates thriving IoT products from costly failures. While most organizations rush to collect every possible data point, successful IoT strategies narrow their focus to just one critical metric that truly matters to customers. This concept, the metric of interest, serves as the North Star for the entire development process, determining which data points you'll collect and which you can safely ignore. Think about it. In a world where a single industrial machine can generate thousands of readings per second, trying to analyze everything is not just inefficient, it's impossible. Yet this is precisely how many organizations approach IoT development. They connect devices, accumulate massive data sets, and only afterward ask, what can we do with all this information? This backward approach explains why so many IoT initiatives end up as expensive experiments that never deliver meaningful returns. The alternative starts with a fundamental shift in thinking. Rather than beginning with, what data can we collect? Successful organizations first identify the specific problem their customers need solved, then work backward to determine which metrics would address that problem. This seemingly minor change in sequence makes all the difference. Consider shipping logistics. In this industry, a particularly hot metric of interest is reliability, specifically when a product will arrive at its destination. Logistics companies understand that customers don't need access to hundreds of data points about their shipments. They primarily want confidence in delivery timing. With this metric clearly identified, the company can focus its IoT strategy on sensors and data points that directly impact arrival predictions, traffic patterns, weather conditions, vehicle maintenance status, and driver behavior. The fitness industry offers another illuminating example. While fitness trackers can measure dozens of biometric signals, many successful products focus specifically on calories burned as their primary metric of interest. This clarity allows them to prioritize the sensors and algorithms that most accurately track energy expenditure during different activities, rather than dispersing resources across every possible health indicator. This focused approach delivers benefits throughout the development process. When you've identified your metric of interest, data collection becomes more strategic. Rather than deploying sensors everywhere possible, you can selectively instrument only the points that influence your key metric. This reduces hardware costs, simplifies maintenance, and prevents data overload. Data processing also becomes more manageable. Instead of building storage and analytics systems capable of handling everything, you can optimize your infrastructure specifically for the data relevant to your core metric. This often means smaller, faster, more cost-effective systems that deliver insights more quickly. Perhaps most importantly, a clear metric of interest dramatically improves user experience. Instead of overwhelming customers with dashboards full of charts and numbers, you can provide a focused interface that highlights the one measurement they truly care about, supplemented by contextual information that helps explain variations in that metric. Identifying this critical metric isn't a task for technologists alone. It requires assembling cross-functional teams that bring together multiple perspectives. Data scientists contribute technical feasibility assessments, helping determine which metrics can be reliably measured and predicted with available technology. Subject matter experts provide domain knowledge about which factors truly impact performance in their field. Marketing professionals bring customer insights, identifying which metrics resonate with users and drive purchasing decisions. This collaborative approach helps organizations avoid the common pitfall of building technically impressive products that solve problems nobody actually has. The diversity of input ensures that the selected metric of interest is both technically feasible and commercially valuable. The evidence supporting this approach is compelling. Research consistently shows that IoT products built around clearly defined metrics significantly outperform general-purpose data collection efforts. Products with focused metrics achieve higher adoption rates, greater user engagement, and better customer satisfaction. They also typically reach market faster and at lower development costs. The contrast becomes particularly stark when examining failed IoT initiatives. A common pattern emerges among unsuccessful projects. They began with ambitious data collection efforts but never clearly defined what problem they were solving or which metric would indicate success. Without this clarity, these projects struggled to deliver value despite accumulating vast amounts of data. Beyond the examples already mentioned, other industries are discovering their own critical metrics of interest. Retailers focus on foot traffic patterns to optimize store layouts and staffing. Transportation planners monitor congestion levels to improve traffic flow. Manufacturing facilities track specific quality indicators to prevent defects. Each successful application starts with clarity about which metric matters most. The advancement of analytics technologies has actually increased the importance of identifying the right metric, not diminished it. Machine learning and AI can find complex patterns in data, but they still require human direction about which patterns matter. Without a clearly defined metric of interest, even the most sophisticated algorithms struggle to deliver actionable insights. This principle, identifying the metric of interest before collecting data, represents a fundamental inversion of how many organizations approach IoT. It embodies the maxim, think first, analyze later. Start by determining which metric would deliver the most value to your customers, then work backward to identify which variables influence that metric, and only then begin sourcing the data needed to track those variables. This disciplined approach doesn't mean ignoring secondary metrics or limiting your long-term vision. Rather, it provides a starting point that ensures your initial IoT deployment delivers immediate value while building the foundation for more complex applications. As you master one metric, you can expand to others, but always with a clear understanding of how each contributes to customer value. Stages 2 to 3. Acquisition and refinement. Taming the data beast. From selling jet engines to selling guaranteed flight hours, GE's transformation challenges everything we thought we knew about industrial companies. Their $6 billion revelation wasn't just about connecting machines to the internet. It was about solving a fundamental data problem that most IoT initiatives fail to recognize until it's too late. When General Electric decided to transform their century-old manufacturing business, they faced a challenge that would test the limits of modern data science. How do you take vastly different machines, jet engines operating at 30,000 feet, wind turbines scattered across remote landscapes, and medical imaging equipment in hospitals worldwide, and create a unified system that extracts actionable intelligence from them all? This wasn't a matter of simply installing sensors. GE's products were already generating mountains of data, but that information existed in incompatible formats, arrived at irregular intervals, and required different contextual understanding to interpret. A temperature reading from a gas turbine meant something entirely different than the same reading from an MRI machine. To address this complexity, GE developed specialized platforms to handle the specific demands of industrial IoT. While many companies attempt to force industrial data into consumer-oriented analytics tools, GE recognized that heavy machinery presents unique challenges that required purpose-built solutions. Their Predix platform became the foundation for optimization and prediction, while they created specialized data integration systems to harmonize the chaotic streams of information coming from their diverse product portfolio. The first stage of GE's transformation, acquisition, required making strategic decisions about sensor deployment. Unlike consumer IoT devices that might track a few basic metrics, industrial equipment demanded hundreds of measurement points to create a complete operational picture. GE's engineers had to determine not just what to measure, but how frequently, under what conditions, and with what precision. This required a delicate balancing act. Too many sensors would create data overload and drain power. Too few would leave blind spots in the analysis. GE's approach involved identifying the critical control points in each machine, the places where small changes in conditions could significantly impact performance or reliability. The connectivity protocols presented another challenge entirely. Consumer IoT typically operates in environments with stable power and reliable internet connections. Industrial machinery, however, often exists in harsh conditions where connectivity is intermittent at best. GE needed to implement robust systems that could function in remote oil fields, aircraft at cruising altitude, and power plants with electromagnetic interference. To solve this problem, GE implemented sophisticated edge computing systems, small but powerful processors, installed directly on equipment that could perform initial analysis before transmitting summarized data to central systems. This approach reduced bandwidth requirements and ensured that critical anomalies could be detected even when cloud connectivity was unavailable. The cloud infrastructure behind these systems represented another innovation. GE built scalable processing capabilities that could handle the sudden spikes in data volume that occur during equipment startup shutdown or anomalous events. The system had to distinguish between routine operational data that could be stored in lower-cost cold storage and critical real-time metrics that required instant accessibility in hot storage. Once acquired, this tsunami of data entered the refinement stage, where GE faced perhaps its greatest challenge. Raw sensor readings contained noise, gaps, and inconsistencies that had to be addressed before any meaningful analysis could occur. These issues ranged from simple calibration errors to complex problems like sensor drift, where measurements gradually become less accurate over time. GE's data scientists developed sophisticated cleansing algorithms that could identify and correct these issues automatically. They implemented normalization processes that converted readings from different sources into standard formats and scales. For instance, what happens when one jet engine reports fuel consumption in gallons per hour while another uses liters per minute? GE's systems had to reconcile these differences to create comparable datasets. Perhaps most impressive was GE's integration of structured and unstructured data sources. While sensor readings provided precise quantitative information, maintenance logs, customer reports, and technician notes offered crucial qualitative context. GE developed natural language processing systems that could extract meaningful insights from these unstructured sources and correlate them with sensor data to provide a complete operational picture. This refined data became the foundation for a radical business model transformation. Rather than simply selling physical products like jet engines, GE began selling guaranteed outcomes like thrust. Airline customers didn't really want to own and maintain complex machinery. They wanted the reliable performance that machinery provided. By combining refined IoT data with predictive analytics, GE could confidently offer performance guarantees that would have been impossible without this data infrastructure. The shift from selling products to selling outcomes changed everything about GE's customer relationships. Service contracts that had once been viewed as necessary expenses became strategic partnerships where both parties benefited from optimal equipment performance. GE's engineers gained unprecedented visibility into how their products performed in real-world conditions, allowing them to identify improvement opportunities that would have remained invisible under traditional business models. This transformation didn't happen overnight. GE invested years building the technical infrastructure and organizational capabilities required to make sense of industrial data at scale. They faced numerous setbacks and challenges along the way, from integrating legacy equipment to convincing skeptical customers of the value proposition. Yet, the results speak for themselves. Approximately $6 billion in annual revenue from software and data products, a figure that would have seemed impossible for a traditional manufacturing company just a decade earlier. The GE case demonstrates how mastering the acquisition and refinement stages creates a foundation for everything that follows. Without properly structured, cleaned, and contextualized data, even the most sophisticated analytics tools produce meaningless results. By investing in these foundational capabilities, GE transformed not just their business model, but their entire approach to customer value. Their journey provides important lessons for organizations at all stages of IoT maturity. First, acquisition strategies must be tailored to the specific operational environment and business objectives. There's no one-size-fits-all approach to sensor deployment, connectivity, or edge computing. Second, refinement isn't merely a technical challenge, but requires deep domain expertise to understand what the data means in context. Technical teams and subject matter experts must collaborate closely throughout the process. Perhaps most importantly, GE's story illustrates how the real value of IoT data emerges when it enables business model innovation. The billions in revenue didn't come from selling sensors or analytics dashboards. They came from reimagining what the company could offer customers once they had mastered these capabilities. Stages 4 to 5, storage and retrieval, building the digital infrastructure. While GE invested millions in their data transformation, today a startup with just thousands could build comparable storage infrastructure. The democratization of cloud computing has silently eliminated what was once an insurmountable advantage of large corporations, but created an entirely new competitive battlefield that few recognize. 20 years ago, if you wanted to build an IoT data product, you needed physical infrastructure, lots of it. Picture massive server rooms with blinking lights, constant climate control, and teams of specialists monitoring hardware performance. Organizations relied on physical media like CD-ROMs for data transfer and local servers with limited storage capacity. These technical limitations created a natural barrier to entry. Only the largest companies with the deepest pockets could afford to build and maintain such systems. Now imagine trying to process data from thousands of sensors generating readings every second. The infrastructure requirements would have been astronomical. The capital investment alone would have stopped most IoT initiatives before they started. This technical reality meant that comprehensive IoT implementations remained theoretical for all but the largest enterprises. But something remarkable happened in the years since: the complete transformation of data storage and retrieval infrastructure. Cloud platforms emerged offering virtually unlimited storage capacity without requiring organizations to purchase a single server. Distributed storage systems enabled data to be spread across multiple locations for redundancy and faster access. These technological shifts fundamentally changed the economics of IoT data management. Today's cloud-based infrastructure allows organizations to start small and scale up as needed, paying only for what they use. This means a startup can access the same enterprise-grade storage capabilities that would have required millions in capital investment just a decade ago. The barriers have collapsed and the playing field has leveled dramatically. But this new landscape requires specialized approaches designed specifically for IoT's unique challenges. Time series databases have emerged as the backbone of effective IoT data storage. Unlike traditional databases optimized for transactions or documents, time series databases are built from the ground up to handle the sequential time-stamped data that sensors produce in abundance. These specialized databases excel at compressing and organizing chronological data, making it possible to store years of historical readings without overwhelming storage capacity. They're designed to handle the specific query patterns that IoT applications require, like identifying trends over time, finding anomalies in operational data, or comparing current values against historical norms. Beyond specialized databases, modern IoT architectures often incorporate data lakes, which allow for the storage of both structured and unstructured data in its raw form. This approach preserves the flexibility to perform different types of analyses without being constrained by rigid database schemas. Engineers can store sensor readings alongside contextual information like maintenance records, weather data, or even social media sentiment that might influence how the data is interpreted. The retrieval side of the equation has evolved just as dramatically. Modern IoT systems rely on application programming interfaces, APIs, that make data accessible to authorized applications and users in real time. These interfaces abstract away the complexity of the underlying storage systems, providing simple methods to query and manipulate data, regardless of where or how it's physically stored. Query optimization techniques have become increasingly sophisticated, allowing systems to retrieve relevant information from massive datasets without scanning every record. This capability is crucial for IoT applications where immediate response times can make the difference between preventing equipment failure and dealing with costly downtime. Perhaps most importantly, today's retrieval systems are designed to handle real-time access patterns. When a critical sensor detects an anomaly, the system can immediately pool relevant historical data for comparison, apply machine learning models to determine the significance, and push alerts to the appropriate personnel, all within seconds. This technological revolution has created an environment where small companies can now compete with enterprises that once held insurmountable advantages. Consider a startup developing smart agriculture solutions. 20 years ago, they would have needed to build their own data centers to process soil moisture readings from thousands of sensors. Today, they can leverage cloud services from providers like AWS, Google Cloud, or Microsoft Azure to handle all their storage and processing needs at a fraction of the cost. Open source tools have further accelerated this democratization. Frameworks like Apache Kafka for streaming data, Prometheus for monitoring, and various machine learning libraries allow small teams to implement sophisticated data pipelines without massive development resources. These tools represent millions of development hours contributed by the global technology community, resources that would have previously been available only to the largest organizations with dedicated research teams. The result is a playing field where innovative ideas can triumph over sheer resource advantages. A small team with deep domain expertise in a specific industry can build IoT solutions tailored to that sector's needs, often outperforming larger competitors with more generic offerings. The technical barriers have shifted from, can we afford to build this, to, do we have the expertise to design this effectively? This democratization has accelerated innovation across industries. In manufacturing, small specialty producers now use the same caliber of predictive maintenance systems once exclusive to industrial giants. Healthcare startups deploy patient monitoring solutions that would have required hospital-sized IT departments a decade ago. Retail entrepreneurs implement inventory tracking systems previously available only to national chains. The real competitive advantage now lies in how effectively organizations use these accessible technologies to enable real-time decision-making. When sensors detect that a machine is operating outside optimal parameters, immediate actions can be taken, adjusting settings automatically, scheduling maintenance before failure occurs, or ordering replacement parts proactively. In transportation logistics, vehicles continuously stream location and condition data, allowing systems to adjust routes in response to changing weather, traffic, or delivery priorities. Agricultural systems monitor soil conditions and automatically adjust irrigation based on current readings combined with weather forecasts. Building management systems optimize energy usage by constantly balancing occupancy patterns against environmental conditions. These capabilities create tangible business benefits, reduced downtime, lower operational costs, improved customer service, and the ability to optimize resources in real time. Organizations that effectively implement these systems gain significant advantages over competitors still relying on periodic reporting and manual interventions. But there's a catch to this democratized landscape. While the technology costs have plummeted, the expertise required to design and implement effective storage and retrieval systems remains a critical competitive advantage. Cloud services may be affordable and accessible, but knowing how to architect systems that balance performance, cost, and reliability requires specialized knowledge. Understanding which data to prioritize for real-time access versus what can be archived in cold storage. Determining the appropriate balance between edge processing and cloud analytics, designing data models that accommodate future use cases without requiring complete rebuilds. These decisions require both technical expertise and domain knowledge, a combination that remains in short supply despite the democratization of the underlying technologies. Organizations that recognize this reality are investing heavily in developing these capabilities, either by building internal expertise or partnering with specialists. They understand that the competitive advantage has shifted from owning infrastructure to mastering its design and implementation. The hardware and software may be commoditized, but the knowledge to deploy them effectively remains valuable. This expertise gap creates both challenges and opportunities. For established organizations, it represents a new area requiring investment and cultural change. For entrepreneurs and specialists, it creates markets for new services and solutions that help bridge the gap between accessible technology and effective implementation. Stages 6-7. Distribution and presentation. The user experience factor. Infrastructure expertise might get your IoT product built, but it's the invisible layer between your brilliant analytics and human understanding that determines whether users will embrace or abandon it. Even the most sophisticated sensor network and analytics engine can be rendered completely ineffective by a single, often neglected factor: the user experience. When we examine the landscape of IoT data products, a fascinating pattern emerges. Technical capabilities often look remarkably similar between wildly successful applications and those that fade into obscurity. The differentiating factor frequently has nothing to do with the underlying data processing prowess, but rather how that information is presented and distributed to users. Consider this surprising statistic. Mobile-first IoT interfaces see adoption rates nearly triple those of desktop-only solutions, regardless of the underlying data quality. This striking difference highlights a fundamental truth about data products. They must meet users where they are, in interfaces they find intuitive and accessible. Technical teams, particularly those with backgrounds in data engineering and analytics, often view distribution and presentation as secondary concerns. Their primary focus remains on the hard technical challenges, building robust data pipelines, optimizing algorithms, and ensuring system performance. This technical bias makes sense on one level. Without solid infrastructure, there's nothing to distribute. However, it creates a dangerous blind spot that has doomed countless IoT initiatives. The evolution of distribution channels for data products tells a compelling story about changing user expectations. We've moved rapidly from physical media to digital platforms, creating numerous new touchpoints for users to interact with IoT data. Modern distribution channels now include dedicated mobile applications, embedded dashboards within existing systems, API integrations allowing data to flow between platforms, and even voice-activated interfaces that make complex data accessible through simple conversations. Each of these channels presents unique design challenges. For instance, APIs require thoughtful documentation and developer support, while mobile applications must operate efficiently on limited screen real estate and potentially unstable network connections. The most successful organizations recognize that distribution isn't just a technical consideration, but a product decision that dramatically impacts adoption. Visualization of IoT time series data presents particularly thorny challenges due to the volume and velocity of the information being processed. Users can quickly become overwhelmed when presented with raw sensor readings or complex dashboards filled with dozens of metrics. Effective visualization requires careful curation and context, transforming numbers into narratives that users can immediately comprehend and act upon. Real-time visualization capabilities have become especially crucial for IoT applications. In industries like transportation and healthcare, monitoring data as it's generated allows for immediate response to changing conditions. The visual presentation of this information must balance comprehensiveness with clarity, showing enough detail to be actionable without creating information overload. Another critical factor is the growing dominance of mobile usage for data applications. This shift necessitates a fundamental rethinking of how interfaces are designed. Mobile-first design isn't simply about shrinking desktop interfaces to fit smaller screens. It requires a complete reconsideration of how users interact with information in different contexts. Mobile interfaces must account for touch-based interaction rather than precise cursor movements, variable network conditions, and often brief engagement sessions. The constraints of mobile devices can actually drive more focused, intentional design decisions that improve the overall user experience. By starting with the most constrained environment, designers are forced to identify the truly essential elements of their data presentation. Device-specific optimization extends beyond just mobile versus desktop considerations. Different screen sizes, operating systems, and input methods all influence how users interact with data products. A dashboard might need to function seamlessly on a plant manager's desktop computer, a technician's tablet, and an executive's smartphone, each presenting the same information but tailored to different use cases and viewing contexts. This optimization challenge extends to ensuring that interfaces remain responsive and performant across various devices. Nothing drives users away faster than laggy interfaces or visualizations that take too long to load. The technical challenge of processing massive IoT datasets must be balanced with delivering a smooth, responsive experience regardless of device capabilities. The research is clear and compelling. User experience directly and dramatically impacts adoption rates of data products. A well-designed interface can make even average data feel valuable, while a poor interface can render even the most sophisticated analytics practically worthless. This relationship between perceived value and presentation quality cannot be overstated. One fascinating case study comes from LinkedIn's People You May Know feature. Initially rejected internally, this data product underwent significant refinement based on user feedback regarding its interface and presentation. After these user experience improvements, it became a key driver of LinkedIn's growth, not because the underlying algorithm improved dramatically, but because the presentation and integration into the user workflow was optimized. The opposite scenario plays out regularly as well. Technically impressive data products fail to gain traction because users find them unintuitive, difficult to navigate, or disconnected from their daily workflows. Without careful attention to how users will actually interact with and derive value from the data, even the most advanced analytics capabilities go unused. This pattern highlights a critical insight. The success of data products depends not just on what they can do, but on how easily users can realize that value. The most effective IoT interfaces don't just display data, they guide users to the most relevant insights and make complex information immediately actionable. Effective distribution and presentation require cross-functional collaboration between data scientists, designers, and subject matter experts. Data scientists understand what's possible, designers know how to make it accessible, and domain experts provide context about how the information will be used in practice. When these perspectives combine, the resulting interfaces bridge the gap between complex data and human understanding. Color choices, typography, information hierarchy, and interactive elements all influence how effectively users can extract meaning from data visualizations. These seemingly superficial design decisions actually determine whether users can quickly identify patterns, outliers, and actionable insights, or become frustrated and abandon the product entirely. For IoT applications specifically, visualization approaches must account for continuous data streams that update in real time. Static charts and graphs are insufficient when monitoring dynamic systems. Interactive visualizations that allow users to explore different time ranges, zoom levels, and data relationships enable deeper understanding than predefined views alone. Another key consideration is the contextual delivery of insights. Rather than requiring users to constantly monitor dashboards, successful IoT products often implement alert systems that proactively notify users when specific conditions are met. This approach respects users' attention as a finite resource, only interrupting them when truly necessary. The relationship between visualization and user trust also warrants attention. When users can easily understand how data is being collected and analyzed, they're more likely to trust and act upon the resulting insights. Conversely, black box systems that provide recommendations without clear explanations often face skepticism and resistance regardless of their technical accuracy. Accessibility considerations further expand the presentation challenge. IoT data products may need to serve users with varying levels of technical sophistication, from data analysts to operational staff to executives. Creating interfaces that remain accessible to non-technical users while providing depth for specialists requires thoughtful design and often multiple complementary views of the same underlying data. Stage 8. Market feedback. Closing the loop. Perfect user interfaces might get your product noticed, but it's what happens after launch that determines whether it thrives or dies. The most valuable IoT products share a surprising characteristic. They're never actually finished. Instead, they evolve continuously through a systematic approach to market feedback that many organizations completely overlook. Let's examine a fascinating case that illustrates this principle perfectly. At LinkedIn, a young data scientist named Jonathan Goldman spotted a potential goldmine in the platform's network data. By analyzing connections between users, he realized he could predict which people members might know but hadn't yet connected with. Goldman developed a feature that would suggest these potential connections, what would later become the People You May Know recommendation system. But when he presented his concept, product owners dismissed it. They believed users already knew who they wanted to connect with and didn't need algorithmic suggestions. This resistance is common with data-driven features, especially when they challenge established thinking about how users interact with products. What happened next reveals the critical importance of feedback loops in product development. Rather than accepting defeat, Goldman persisted. He advocated for testing the feature with actual users to let real behavior, not internal opinions, determine its value. After gaining support from co-founder Reid Hoffman, Goldman deployed a basic version of the recommendation system. The results were striking. Users immediately engaged with the suggested connections at rates far exceeding expectations. What seemed unnecessary to product owners proved invaluable to actual users. The feature ultimately became responsible for approximately half of LinkedIn's member growth, a staggering impact from a feature that almost never saw the light of day. This story highlights something crucial about successful IoT products. They require closing the feedback loop between market reactions and product development. While technical excellence in data acquisition and processing is essential, equally important is the systematic collection and integration of user feedback. Modern IoT companies have developed sophisticated methods for gathering this crucial market intelligence. A/B testing has emerged as a particularly powerful approach, allowing product teams to deploy different versions of features to different user segments simultaneously. This controlled experimentation provides statistically significant data about which implementations drive desired user behaviors. Usage analytics offer another crucial feedback mechanism by carefully tracking how users interact with interfaces, navigation patterns, feature engagement rates, and session durations. Companies can identify both friction points and opportunities for enhancement. These behavioral insights often reveal surprises. Features developers assumed would be popular may go unused, while seemingly minor elements might prove essential to the user experience. Direct user feedback channels provide qualitative context that numbers alone can't capture. Structured interviews, focus groups, and feedback forms help product teams understand the why behind user behaviors. For instance, a smart home system might track that users frequently adjust thermostat settings manually even after programming schedules, but only through direct feedback might developers learn this occurs because the interface for creating schedules is too complicated. Behavioral analysis represents perhaps the most sophisticated form of feedback. By examining patterns in how different user segments interact with products over time, companies can identify emerging needs and preferences. This approach often reveals opportunities for new features before users themselves can articulate what they want. More recent innovations have expanded the feedback toolkit further. Crowdsourcing techniques invite users to actively participate in product evolution, sometimes by voting on potential features or even contributing to their development. Flash surveys delivered at key moments within product experiences can gather time-sensitive feedback precisely when users are engaged with specific features. What truly distinguishes market leaders, however, is not just collecting feedback, but systematically feeding these insights back into the product development cycle. This creates what experts call a closed-loop system, where market reactions directly inform ongoing product refinement. Rather than treating feedback as occasional input, successful IoT companies establish formal processes to ensure market intelligence continuously shapes product evolution. The most effective implementations integrate feedback directly into the product conceptualization stage. When considering new features or refinements, teams begin by examining existing user behavior patterns and explicitly stated needs. This ensures that development efforts focus on solving actual problems rather than creating impressive but ultimately unnecessary capabilities. Implementing this closed-loop approach often requires navigating significant organizational challenges. The LinkedIn story demonstrates a common pattern. Data-driven insights frequently face resistance from stakeholders who rely on intuition or past experience. Data scientists and product managers must develop stakeholder management skills to advocate effectively for market-validated approaches. Cross-functional collaboration becomes essential in this environment. Engineering teams must work closely with user experience designers, data analysts, marketing specialists, and business stakeholders. This integration ensures that technical capabilities align with market needs and that customer insights drive development priorities. Research consistently demonstrates the power of this approach. Products with integrated feedback mechanisms significantly outperform static offerings across virtually every metric, from adoption rates and user engagement to customer satisfaction and revenue generation. One study found that IoT products employing continuous feedback-driven iteration achieved 37% higher customer retention rates than those following traditional development models. This performance differential stems from the fundamental nature of how people interact with technology. User needs and expectations evolve constantly, especially in rapidly developing fields like IoT. A product that perfectly meets market requirements today may become obsolete within months as expectations shift. Only through continuous feedback-driven refinement can products remain relevant. The implications for IoT product development are profound. The most valuable products in this space are never truly finished in the traditional sense. Instead, they exist in a state of perpetual evolution, adapting to changing user requirements and technological capabilities through structured feedback loops. This represents a fundamental shift from traditional product development approaches. Rather than investing enormous resources in developing perfect products before launch, successful IoT companies deploy viable products quickly, then systematically refine them based on real-world usage. This iterative approach reduces initial development costs while increasing the likelihood of creating truly valuable solutions. For organizations building IoT data products, implementing this feedback-driven approach requires specific capabilities. Teams need technical infrastructure to collect and analyze user behavior data. They need organizational processes to translate insights into development priorities. Perhaps most importantly, they need a culture that values empirical market feedback over internal opinions. The LinkedIn example demonstrates another crucial aspect of feedback-driven development: persistence. Transformative features often face initial skepticism, requiring champions who believe in testing concepts with actual users. Had Goldman simply accepted the initial rejection, LinkedIn would have lost a feature that drove half its member growth. This highlights the importance of creating organizational environments where data scientists and product developers can advocate for testing promising concepts even when they challenge conventional thinking. Companies that create pathways for market testing innovative ideas gain significant advantages in the IoT landscape. Case study: Progressive Insurance, monetizing driving behavior data. Conventional wisdom in insurance pricing relied on demographic data and credit scores until one company decided to challenge the entire paradigm. What if your actual driving behavior, not just who you are on paper, could determine what you pay for car insurance? Progressive Insurance didn't just ask this question, they built a multi-billion-dollar business answering it through their groundbreaking Snapshot program. While traditional industries often lag behind tech giants in data innovation, Progressive took the 7-stage data refinement framework we've discussed and implemented it with remarkable precision. Their approach transformed a simple device plugged into your car's diagnostic port into one of the most successful IoT data products in the conventional industry. The genesis of Progressive's innovation began with a fundamental insight about their core business. Insurance companies have always been in the prediction business, attempting to assess the likelihood of accidents and price policies accordingly. For decades, the industry relied on proxies like age, gender, location, and credit scores to estimate risk. Progressive hypothesized that direct measurement of actual driving behavior might yield more accurate predictions. This hypothesis led them to identify the perfect metric of interest: driving behavior as a predictor of accident risk. Their research confirmed this intuition dramatically. Actual driving patterns proved approximately 25% more predictive of crash likelihood than traditional credit scores. This single insight opened the door to an entirely new business model. With their metric of interest clearly defined, Progressive designed an elegant acquisition strategy centered around a simple device that plugs into the OBD2 port found in most vehicles manufactured after 1996. This unassuming piece of hardware captures critical data points including heart-breaking frequency, rapid acceleration patterns, and the times of day when the vehicle is in operation. Unlike complex industrial IoT implementations requiring hundreds of sensors, Progressive identified just a few key variables that meaningfully correlate with accident risk. This focus allowed them to keep the hardware costs manageable while collecting only the most relevant data. A perfect example of how identifying the right metric simplifies the entire data collection process. The acquisition phase also had to overcome significant logistical challenges. Progressive needed to deploy millions of these devices to customers nationwide, ensure they were properly installed, and maintain reliable data transmission from vehicles operating in widely varying conditions. Their solution involved creating a simple self-installation process with clear instructions and customer support, minimizing friction in the data collection process. Once the raw driving data began flowing into Progressive systems, the refinement stage took center stage. The company faced the challenge of transforming millions of individual driving events into meaningful risk profiles. Their data scientists developed sophisticated algorithms to normalize driving data across different vehicle types, road conditions, and geographical locations. The refinement process also incorporated contextual data that significantly enhanced the value of the raw sensor readings. For example, a sudden deceleration might indicate aggressive braking behavior, or it might simply reflect a driver responding appropriately to an unexpected road condition. By integrating map data, traffic patterns, and weather information, Progressive's algorithms learned to distinguish between these scenarios, further improving their predictive accuracy. Progressive's approach to storage and retrieval balanced the need for historical analysis with real-time decision-making capabilities. Their systems needed to maintain comprehensive driving histories for each customer while simultaneously providing immediate feedback through their mobile applications. This required a sophisticated data architecture capable of processing both streaming data for immediate analysis and archival data for ongoing refinement of their risk models. The distribution and presentation stages represented another area where Progressive excelled. Rather than keeping their insights locked in internal systems, they created multiple customer-facing channels to share relevant information. Their smartphone application transformed complex driving data into intuitive visualizations and actionable feedback, showing drivers how specific behaviors affected their potential discounts. This transparency in the distribution stage created a powerful alignment of incentives between Progressive and their customers. Drivers who received feedback about harsh braking or excessive acceleration could modify their behavior, simultaneously reducing their accident risk and qualifying for lower premiums. The data product thus created value for both the company and its customers, a hallmark of successful IoT implementations. The presentation layer of the snapshot program deserves particular attention. Progressive's designers recognized that simply dumping raw driving statistics on users would create confusion rather than engagement. Instead, they developed intuitive scoring systems, progress indicators, and specific behavioral feedback that translated complex data analysis into clear, actionable information for drivers. Perhaps most impressively, Progressive built a robust market feedback loop that continuously improves their product. Every time a snapshot customer is involved in an accident, or more importantly, avoids one, the system gains valuable data about the relationship between driving behaviors and actual outcomes. This closed-loop approach has allowed Progressive to refine their algorithms continuously, creating an ever-widening competitive advantage. The market feedback stage also informed product evolution beyond the initial OBD device. As smartphone technology advanced, Progressive expanded Snapshot to include mobile app-based monitoring, eliminating the need for physical hardware in many cases. This evolution, driven by user feedback about installation friction, illustrates how effective feedback loops can drive product improvements across multiple dimensions. Today, Progressive's data collection has expanded to approximately 10 billion miles of driving information, a proprietary dataset that represents an enormous competitive advantage. This data repository allows them to identify increasingly subtle correlations between driving patterns and accident risk, enabling ever more precise personalization of insurance pricing. The financial impact of this data product has been remarkable, generating approximately $2 billion in insurance premiums, but the strategic value extends far beyond direct revenue. The Snapshot program has positioned Progressive as an innovator in a traditionally conservative industry, attracted safety-conscious drivers to their customer base, and created switching costs that reduce customer churn. Progressive's implementation demonstrates how the 7-stage framework can transform a traditional industry through data-driven innovation. By starting with a clear metric of interest, designing efficient acquisition methods, refining raw data into valuable insights, building effective storage and retrieval systems, creating engaging distribution and presentation layers, and establishing robust feedback mechanisms. They built a complete data value chain that continues to deliver competitive advantages. The success of Snapshot also highlights the importance of organizational factors beyond technical implementation. Progressive's leadership created an environment where data scientists could challenge industry assumptions, test radical new approaches, and receive the resources needed to scale promising concepts. This cultural willingness to question conventional wisdom proved just as important as their technical capabilities. Looking beyond Progressive's specific implementation, their success offers broader lessons for organizations in any industry. First, it demonstrates that IoT data products can thrive in traditional sectors, not just tech companies. Second, it shows how focusing on a specific high-value metric allows for targeted data collection rather than capturing everything possible. Finally, it illustrates how creating value for both the organization and its customers creates sustainable competitive advantages. Challenges and ethical considerations in IoT data monetization. While Progressive's successful IoT program demonstrates how data can transform traditional business models, beneath the surface of this digital revolution lurks a complex web of ethical dilemmas. Imagine a world where your smart toothbrush silently monitors your brushing habits, recording duration, pressure, frequency, and even which quadrants of your mouth receive the most attention. This seemingly innocuous data might be shared with your dentist, who adjusts your treatment plan accordingly. But what happens when that same data is simultaneously transmitted to your dental insurance provider, who raises your premiums based on insufficient oral hygiene practices? Or to toothpaste manufacturers who target you with increasingly urgent marketing messages? This scenario isn't science fiction. It represents the fundamental tension at the heart of IoT data monetization. As billions of devices track our most intimate behaviors, from sleeping patterns to medication adherence, we're forced to confront uncomfortable questions about the boundaries between valuable personalization and invasive surveillance. The challenge for companies creating IoT data products isn't just technical, it's deeply ethical. For every data point collected, organizations must navigate complex considerations around consent, privacy, and trust. This balancing act grows increasingly difficult as the number of connected devices in our lives multiplies exponentially. Data ownership represents one of the most significant unresolved challenges in the IoT ecosystem. When a consumer purchases a smart refrigerator, who owns the data it generates? Is it the manufacturer who built the device, the software company that powers its analytics, or the consumer whose behavior is being monitored? This question becomes especially thorny when data from multiple sources is combined to create new insights that weren't possible from any single device. The absence of standardized ownership frameworks has led to a patchwork of approaches. Some companies claim ownership of all data generated by their devices through extensive terms of service agreements that consumers rarely read. Others have adopted more collaborative models that acknowledge shared ownership rights while establishing clear guidelines for usage. Closely related to ownership is the issue of informed consent. Traditional consent mechanisms, typically involving lengthy legal documents and a single checkbox, have proven woefully inadequate for IoT environments. How can users meaningfully consent to data collection when they may not understand the full scope of what's being gathered or how it might be used in the future? The most innovative companies in this space are reimagining consent as an ongoing conversation rather than a one-time transaction. These approaches include layered consent models that allow users to approve different levels of data sharing for different purposes, and dynamic consent systems that notify users when new types of data collection are introduced or when existing data is being used in novel ways. The security vulnerabilities inherent in many IoT devices compound these privacy concerns. Many connected products are manufactured with minimal security protections, creating what security experts call soft targets for malicious actors. A compromised smart home device can expose not just the data it collects, but potentially serve as an entry point to an entire network of connected systems. The regulatory landscape addressing these challenges continues to evolve, though often at a pace that lags behind technological innovation. The European Union's General Data Protection Regulation, GDPR, established important precedents for personal data protection, including requirements for explicit consent and the right to be forgotten. Similarly, the California Consumer Privacy Act, CCPA, provides consumers with greater control over how their personal information is collected and used. These frameworks impose significant obligations on organizations that collect and process IoT data, including requirements for comprehensive data protection, impact assessments, and procedures for responding to user requests to access, correct, or delete their information. Companies operating globally face the additional complexity of complying with varying and sometimes contradictory regulations across different jurisdictions. Forward-thinking organizations have recognized that addressing these challenges isn't just about regulatory compliance, it's a strategic imperative. Approaches that build consumer trust can create sustainable competitive advantages in increasingly crowded markets. Opt-in models represent one of the most straightforward ways companies are addressing privacy concerns. Rather than assuming users want all available features and the associated data collection, these models require explicit permission before gathering information. While this approach may reduce initial data collection volumes, research suggests it often leads to higher quality data from more engaged users. Anonymization techniques offer another promising approach, allowing organizations to derive valuable insights without compromising individual privacy. These range from simple methods like removing personally identifying information to more sophisticated techniques like differential privacy, which adds carefully calibrated noise to datasets to protect individual records while preserving statistical validity. Transparent data usage policies have emerged as another best practice, with companies clearly communicating what data they collect, how it's used, and who has access to it. The most effective policies avoid legal jargon in favor of simple, direct language that helps users understand the practical implications of their choices. The business consequences of mishandling these considerations can be severe. Companies that experience major privacy breaches or are perceived as exploiting user data often face immediate backlash in the form of lost customers and damaged brand reputation. These impacts can persist long after the initial incident, as rebuilding trust typically requires sustained effort over extended periods. Beyond reputational damage, organizations may face significant regulatory penalties for non-compliance with data protection laws. Under GDPR, for example, violations can result in fines of up to 4% of global annual revenue, a potentially existential threat for many businesses. Perhaps most importantly, research increasingly suggests that privacy-preserving approaches can actually enhance user trust and encourage greater data sharing. When consumers believe their information is being handled responsibly, they are more likely to engage with IoT products and share the data necessary to create valuable personalized experiences. This dynamic creates a virtuous cycle where respect for privacy leads to higher user engagement, which in turn enables more effective and valuable data products. Companies like Apple have successfully differentiated themselves in the market by emphasizing privacy as a core feature rather than treating it as a regulatory burden. The most successful implementations of IoT data products integrate privacy considerations from the earliest stages of the design process. This privacy by design approach involves considering potential privacy impacts at each stage of development, from initial concept through implementation and beyond. By addressing privacy as a core design principle rather than an afterthought, organizations can build data products that create value while respecting fundamental human rights to privacy and autonomy. This approach often leads to more elegant solutions that achieve business objectives without unnecessary data collection or invasive monitoring. The healthcare sector provides illuminating examples of this balance. Remote patient monitoring systems can track vital signs and medication adherence, potentially improving outcomes and reducing costs. However, this same technology raises profound questions about surveillance and autonomy, particularly for vulnerable populations like the elderly or chronically ill. Organizations that have successfully navigated these challenges typically involve diverse stakeholders, including ethicists, privacy advocates, and patient representatives in their design processes. They explicitly consider questions of power, consent, and dignity alongside technical requirements and business objectives. Democratizing the IoT data economy. Opportunities for all. The democratization of IoT technology represents a profound shift in who can participate in the data economy. While tech giants dominated early IoT development with their massive R&D budgets and extensive resources, a quiet revolution has been unfolding beneath the headlines. Today, organizations of every size have unprecedented access to the tools and technologies needed to create valuable IoT data products. This technological democratization isn't just theoretical, it's reshaping the competitive landscape in real time. The same cloud infrastructure that powers Fortune 500 companies is now available to small businesses through affordable, scalable solutions that eliminate the need for substantial upfront investments. This fundamental shift means that success in the IoT space is increasingly determined by vision and specialized knowledge rather than sheer organizational size or financial resources. What's particularly striking about this evolution is how it removes the traditional barriers that once prevented smaller players from entering data-intensive markets. Just a few years ago, building IoT infrastructure required dedicated server farms, specialized hardware, and teams of engineers just to manage the basic plumbing of data collection. Today, a small business can leverage affordable sensors, open-source analytics tools, and cloud-based processing capabilities to build sophisticated data products at a fraction of the historical cost. The hardware side of this equation has seen dramatic improvements in both capability and affordability. Sensors that once cost hundreds of dollars have been miniaturized and mass-produced, bringing their price points down to levels accessible for even modest projects. These sensors can measure everything from temperature and humidity to complex biometrics, and their decreasing size and power requirements make them suitable for embedding in virtually any product or environment. Meanwhile, the software foundation for IoT development has become increasingly accessible through open-source tools and platforms. Frameworks for data collection, processing, and analysis that would have required millions in development just a decade ago are now freely available to anyone with the expertise to implement them. These tools provide smaller organizations with capabilities that rival those of much larger enterprises, allowing them to focus their limited resources on developing unique solutions rather than building basic infrastructure. Perhaps most significantly, cloud computing has completely transformed the economics of IoT data storage and processing. Small and medium-sized businesses can now access virtually unlimited computing resources on a pay-as-you-go basis, scaling their operations up or down as needed without significant capital expenditure. This flexibility is particularly valuable for organizations exploring IoT applications, as it allows them to experiment without committing to major infrastructure investments before proving their concepts. But the democratization of IoT isn't just about access to technology, it's also creating new competitive dynamics that often favor smaller, more specialized organizations. While large enterprises certainly maintain advantages in scale and resources, smaller organizations can leverage unique strengths that give them surprising advantages in specific IoT niches. Domain expertise represents one of the most powerful competitive edges for smaller organizations entering the IoT space. A specialized manufacturing firm with decades of experience in a particular industrial process may have insights about relevant data collection points that would take a tech giant years to develop. This deep understanding of specific industries or processes allows smaller players to identify the truly valuable metrics that larger, more generalized competitors might miss. Agility provides another critical advantage. Smaller organizations can typically move from concept to implementation much faster than their larger counterparts, allowing them to respond quickly to emerging opportunities or changing market conditions. While a major corporation might need months to navigate internal approvals for a new IoT initiative, a small business can often execute in weeks, giving them a first-mover advantage in rapidly evolving markets. The focused customer relationships that characterize many smaller businesses also create unique opportunities in the IoT space. These organizations often have direct personal connections with their customers, giving them deeper insights into pain points and unmet needs. This intimate understanding of customer challenges can guide more precise IoT product development, resulting in solutions that address specific problems rather than generic data collection efforts. We're already seeing compelling examples of small and medium businesses successfully creating valuable IoT data products across various industries. These case studies demonstrate how domain knowledge combined with focused innovation can produce solutions that large organizations might overlook due to their size and complexity. One particularly illustrative area is emerging in everyday consumer products. Companies are beginning to embed sensors in items as commonplace as toothbrushes, creating devices that can track usage patterns and provide feedback on oral hygiene habits. These seemingly simple applications demonstrate how smaller firms with specialized knowledge can find unique opportunities to create value from IoT data, even in established product categories. Similar innovation is happening in specialized business domains where niche expertise creates opportunities for IoT applications, from agricultural sensors that monitor soil conditions for specific crops to specialized equipment monitors in manufacturing environments. Smaller organizations are finding ways to create valuable data products tailored to the precise needs of their markets. Interestingly, this democratization doesn't mean that creating successful IoT data products has become effortless. While technology access has been revolutionized, the expertise needed to leverage these tools effectively remains a significant barrier. The primary obstacle for most smaller organizations isn't access to sensors or cloud infrastructure, it's having the right skills to turn those resources into valuable products. The skills required for effective IoT product development span multiple domains, creating challenges for organizations with limited personnel. Data management capabilities are essential for handling the volume and variety of information generated by connected devices. Analytics expertise is needed to extract meaningful insights from raw sensor data. Perhaps most importantly, successful IoT initiatives require effective collaboration among cross-functional teams, bringing together technical capabilities with domain knowledge and business strategy. This skills gap, rather than technology limitations, represents the true barrier to entry for many organizations. While cloud platforms and affordable sensors provide the foundational infrastructure, turning these resources into valuable data products still requires specialized knowledge that many smaller organizations lack. This creates both challenges and opportunities, as businesses that can develop or acquire these skills gain significant advantages in their markets. What makes this situation particularly interesting is that it suggests a future where success in the IoT data economy is determined less by organizational size and more by vision, expertise, and execution. The playing field hasn't been completely leveled. Large organizations still maintain important advantages in resources and scale, but the barriers have been lowered enough that innovative smaller players can carve out valuable positions in specific niches. This evolution creates new imperatives for organizations of all sizes. For smaller businesses, the opportunity lies in leveraging their domain expertise and agility to create targeted IoT solutions that address specific customer needs. Rather than attempting to compete directly with tech giants on broad platforms, these organizations can focus on specialized applications where their industry knowledge creates unique advantages. For larger enterprises, the democratization of IoT technology means facing potential disruption from more nimble competitors with specialized expertise. These organizations need to find ways to combine their advantages in scale and resources with the agility and domain focus that characterize successful smaller players in the IoT space. What's becoming increasingly clear is that the future of the IoT data economy will be shaped by organizations that can effectively combine technical capabilities with domain expertise, regardless of their size. The most successful products will come from teams that understand both the possibilities of the technology and the specific needs of their customers, creating solutions that transform raw data into genuine value. It's clear we are no longer speculating about the future of IoT. We're witnessing its economic impact now, with software and data products in this sector generating approximately $6 billion this year alone. This represents real value creation happening across industries right now. The 7-stage refinement framework we've explored isn't just theoretical, it's being implemented by forward-thinking organizations that recognize the strategic advantage of transforming sensor data into products customers genuinely value. The divide is growing between those who've developed sophisticated data refinement capabilities and those still treating IoT as merely a collection of connected devices. Your organization's success in this new economy won't be determined by size or resources, but by how quickly you can establish the expertise to convert raw data into meaningful solutions that address specific customer needs.